Hi, this is Professor Fernandez, and this is video 2 in lesson 14. So we're still talking here about optimization theory, but now we've moved on to thinking about global extrema. So I'm going to run through this example 4.19 from Calculus Simplified to get you used to those concepts. So I do want to mention that we are going to be using concepts that have appeared in previous videos. Specifically, we will be finding critical points and numbers for this example. So that was covered in video 13.5 if you want to go there for a review. This example says find the absolute extrema of this function on this interval. So if you are unfamiliar with this phrase, right, unlike local extrema, which we covered in video 14.1, absolute extrema are the highest y value of the graph on the interval that's given, and the lowest y value of the graph on the interval that's given. So those are the absolute extrema of the graph. There may be more than one, for example, like for a sine graph or something, right? Then, there may be more than one equal maximum value. There may be more than one equal minimum value. But the point is that absolute refers to the highest possible, either y value or, the lowest possible, the highest possible y value, which is maximum, absolute maximum, or the lowest possible y value, that's the absolute minimum. How do we go about finding these? Well, I've put down here box 4.4 in the book, Calculus Simplified. And this is very useful, and it's the most common case when you are finding the absolute extrema of a continuous function that's defined on a closed interval a,b. I'm also going to assume, as is usually the case, that the function is not only continuous, but you have enough smoothness that you can differentiate it and find the critical numbers and things like that. So the first step is usually to find the critical numbers inside the open interval AB, meaning you don't look at the endpoints. Why? Because the second step is to calculate the critical values. In other words, what is f of whatever critical number you found, and also calculate the y values of the endpoints. The idea here, as I explain in the book, is basically that if you're looking for, if I just draw a function, right, and maybe the function looks like that. Here's A and here's B. And then you can see just from this graph that this is the absolute maximum, capital M, and this is the absolute minimum, capital lowercase m. But there are a bunch of points in the middle that are candidates, right? If I didn't give you the graph and I just gave you the equation, these local maxima would be candidates for the absolute maximum. These local minima would be candidates for the absolute minima. So, we got to find those local extrema, which we do with the aid of the critical numbers, because they're candidates for the absolute extrema. And then we got to compare their y values to the y values of the endpoints, right? And that's step number 2. After that comparison of y values, we can then say step number 3, the absolute max is the largest of the numbers that we got from those comparisons, and the absolute minimum is the smallest. Okay, so let me zoom out and show you how that works for this particular example. So let's put that all into practice. All right, so the function we're dealing with here is x squared minus 1 quantity cubed, and this is our interval. So step number 1 down here, find the critical numbers. So I need to take the derivative of this function. So you could multiply this out. It would take a pretty long time. No need to do that. We can differentiate it as a composite function using the chain rule. Derivative of the outside, that's something cubed, so the derivative is 3x squared. Evaluated at the inside times the derivative of the inside, 2x. Okay, so that is our f prime. And then I can just simplify that a little bit. I get 6x times x squared minus 1 squared. Okay, so now what do we do with that? Well, we still want to find the critical numbers. So there are 2 things that we want to do. We want to set this equal to 0, and we want to also ask, are there any x values where this function is not defined? Like I said in this earlier video, 14.1, this is usually the easier question because most of the time the answer is no. There are no values where this function is not defined. And most of the reason why that's true is because usually you're dealing with a polynomial. Polynomials are defined everywhere, no vertical asymptotes, things like that. So there are no x values where the function f prime of x is not defined. So let's do this now. Let's set it equal to 0 to find our critical numbers. Okay, setting this equal to 0, what do I get? Well, so if this part is set equal to 0, that yields x equals 0. That's one critical number. And now I'm going to set this equal to 0. x squared minus 1 squared equals 0. All right, so if I just take the square root of both sides, right, I get rid of the square and I would get x squared minus 1 equals 0. I can factor the left-hand side into x minus 1, x plus 1, because this is a difference of squares, x squared minus 1 squared. And then I set these equal to 0, and that gives me x equals -1 and x equals 1. So I have 3 critical numbers. Now let's go on to the next part of our box 4.4 procedure. So I have my critical numbers. This is me trying to make more room so we can do the second part. Almost done here. There we go. Okay, so next part of the procedure down here. Calculate the critical values. Let's do that. What does that mean? That means you substitute these x values into the function. Right? The critical values are the y values of the critical numbers. So this is my function. So I'm putting in x equals 0, for example, here. So I get 0 squared, that's 0, minus 1, that's -1, -1 cubed, -1 cubed. That's -1. I go back and I do the same thing, but I plug in -1. I square -1, I get 1. I subtract 1, I get 0. So that's 0. And then how about 1? So I put in 1 here, I square it, I get 1. Subtract 1, I get 0 again. Okay, so these are my critical values. And the next part in my procedure says, okay, we did half of it. Calculate the associated critical values, done, and then calculate f of a and f of b. All right, so what is a in this case? Negative square root of 2. We'll calculate that in a minute. What is b in this case? Square root of 2, right? The right endpoint. So now we're going to calculate these values. So if I square negative square root of 2, the negative turns positive, the square root of 2 turns into 2. So I have 2 minus 1, that's 1, cubed is 1. There we go. And then if I go back and I do it again, because it's x squared, when I do it for square root of 2, I'm going to get the same answer. The square is 2, minus 1 is 1, cubed is 1. So this is, again, 1. Now I have all of my y values. So I did step 1, did step 2, and number 3. The absolute max is the largest of the numbers in this step. So I'm going to scan around. What is the largest number? Scanning these right here. So that is the absolute maximum. So 1, y equals 1 is the absolute maximum. And it occurs at the endpoints. You can see the graph down here that I will refer to in a minute. Okay, and then the absolute minimum is the smallest of these numbers. So I'm scanning here again for the smallest. There it is, right? And that occurs at x equals 0. So my conclusions, absolute max of y equals 1 at x equals plus or minus square root of 2. That's this part, right? These two. And then absolute min of y equals -1, that's this one, at x equals 0 over here. Okay, let's see if that matches with the graph of the function. So I've included that down here. This is the graph of the function. I'll zoom in a little bit. On the interval over here is square root of 2. Over here is negative square root of 2. And then let's see if these conclusions match. Let's look at the absolute maximum. It should be y equals 1 at the endpoints. Here's y equals 1. Here's the right endpoint. Here's the left endpoint. That is the maximum y value on the graph. Awesome. Go back. How about the absolute minimum of y equals -1 at x equals 0? Okay, and look at the graph. Y equals -1 at x equals 0. Absolute minimum, smallest y value on this graph. Awesome. Check again. Okay, so this has been a quick video to show you how you would apply this procedure down here in box 4.4 to find the absolute extrema of a function on a closed interval. There are other ways to find the absolute extrema, other procedures. I won't cover that in this video, partly because I think this is probably the simplest one. You just find the critical numbers. That involves taking derivatives and finding where the derivative is 0 or undefined. Then you calculate the y values at those numbers you found. That's what we did over here. And then basically you add in the y values at the endpoints and then you compare. Right? That's a pretty straightforward procedure. The largest y value gives you your max. The smallest y value gives you your min. And then you say, great, I'm done with this problem. Okay, thanks for watching.